Hi, my name is Erica Knorr, and I will be presenting on our recent article in Journal of Photochemistry and Photobiology entitled Excited State Proton Transfer Dye with an Emission Quantum Yield up to 60% upon Zn2 plus coordination. In this study, we used an ESIPT dye known as 2,5-bis-2-pyridylamino-4,7-dihydroxyisoindole as a fluorometric metal ion sensor. When this chromophore is photoexcited, the electron density shifts from the phenolic protons toward the imine nitrogen, which leads to an excited state proton transfer from oxygen to nitrogen. The dye then emits from the proton-transferred keto state, which has a different wavelength than if it had instead emitted from the enol state. ESIPT dyes are useful as fluorometric sensors because they exhibit a large Stokes shift in emission, can act as turn-on or turn-off sensors in the presence of analytes, and are sensitive to environmental conditions such as solvent and pH. For this project, we used 2,5-bis-2-pyridylamino-4,7-dihydroxyisoindole, here on out referred to as molecule 2, as a metal ion sensor. This molecule has two potential ESIPT sites as well as a 1,3-bis-2-pyridylamino-isoindole core, and both the ESIPT sites and the core have the potential to bind with metal cations. The questions then become, what effects do metal cations have on the absorption and emission of the dye, and to which site do these metal cations bind? To address the question of the effects that metal cations have on the photophysics of molecule 2, absorption and emission measurements were performed. Molecule 2 is soluble in DMSO, but to make the sensing environment more relevant to biological samples, absorption and emission measurements were performed in a 90-10 mixture of DMSO and water. Molecule 2 experienced only a nominal shift in its absorption and emission spectra upon the addition of barium, calcium, cadmium, iron, magnesium, manganese, and strontium dications, indicating that these metals likely do not bind to the chromophore. However, the addition of mercury, zinc, cobalt, copper, and nickel dications caused a bathochromic shift in the absorption, which suggests that these four cations do bind to the molecule. Additionally, higher concentrations of mercury and cobalt result in a color change for molecule 2. Mercury, nickel, cobalt, and copper dications were shown to quench the emission of molecule 2. However, the addition of Zn2 plus causes a bathochromic shift in the emission wavelength and increases the emission quantum yield from 25 to 60%. Molecule 2 exhibits spectral broadening and shifts in absorption maxima upon metal ion coordination. These trends are similar to those exhibited by molecule 1, which lacks the ESIPT sites. But how do these metal cations bind to molecule 2? To answer this question, we performed a titration of molecule 2 with Zn2 plus and took NMRs at 10, 20, 30, and 50 equivalents of zinc. During this titration, the A protons next to the phenolic groups did not shift or disappear. However, the B, C, D, and E protons at the core all shifted, and the F proton disappeared entirely. These changes, along with the fact that molecule 2 exhibits spectral broadening and shifts in absorption similar to those in molecule 1, which again lacks an ESIPT site, suggest that Zn2 plus binds to the core sites in a tridentate coordination with molecule 2 and does not bind to the ESIPT site. A Joe plot was also generated, which showed that 2 of molecule 2 will coordinate with one zinc cation. We further probed the application of this dye as a turn-on fluorescent probe by synthesizing a derivative known as molecule 4, which has protecting groups at the ESIPT sites. When added to a solution containing molecule 4, hydrazine cleaves the bromobutyrate protecting group. This results in bright red emission, which continues to increase in intensity for about 20 minutes. The addition of hydrazine generates the deprotonated form of molecule 2, allowing for emission from the keto state while bypassing excited state proton transfer. Overall, molecule 2 will exhibit spectral shifts in the presence of mercury, zinc, nickel, cobalt, and copper 2 plus ions. While most of these metals will quench the emission, Zn2 plus increases the emission quantum yield of molecule 2 to 60%. Metal cations coordinate with molecule 2 via the core nitrogens rather than the ESIPT site. With the addition of protecting groups at the ESIPT sites, molecule 4 can also be used as a turn-on fluorescent sensor with hydrazine because it will cleave the protecting groups from the phenolic positions. If you would like to hear more about the Hansen Research Group, follow us on Twitter and Instagram at HansenFSU. Thanks for listening.